Team, let's talk now about Doppler effect. So the Doppler effect is an analysis of sound traveling through a medium. We understand that because it is traveling through a medium, it also has a speed. That's where the speed of sound comes in. We generally make the assumption that the speed of sound travels at 343 meters per second, and you can find that on the PRC. But if it doesn't, we'll give you the number as well in this situation. We also have to remember that velocity, when it comes to waves, is equal to the wavelength times the frequency. So we can use this understanding to explain how it works here between two people. So in this situation, we have the source, and the source is standing still. The observers are also standing still. Notice that they are both receiving the sound at the same frequency, meaning like, okay, so 1, 2, 3, 4. They're both receiving it at the same frequency, one after the other. Because they're both receiving at the same frequency, they are also getting it at the same velocity, or the same speed, and the same wavelength as well. Because we only were, like this time around, the only thing that is being affected, like the only thing that is affecting sound is the speed of sound. It is the medium in which it is traveling, nothing else. Okay? Let me write this down right here. All right, so now in the part B, moving source and stationary observers, in this situation, the car is moving towards the woman. Notice how the lines here start becoming closer and closer to each other. It means two things. It means, because they're getting closer to each other, it means that the frequency is increasing for the woman. And also it means that because they're going closer to each other, the wavelength of the sound is decreasing, but the speed of sound stays the same. Now the situation is the same with this man right here, but he is experiencing longer, like it's hitting him shorter, longer frequency. So it means that the frequency is decreasing because of the distance here. Notice the distance compared to the distance right here, but the wavelength is increasing. So in this situation, for this man, so the frequency observed, he's actually getting a lower frequency observed than this woman that's getting a higher frequency observed. Okay, now in this last part right here, it's the same thing. This man is getting lower frequencies because he's moving away from the source. Okay, but this woman is getting higher frequency because she's moving away, closer. She's moving closer to the source. Okay. All right, so I was asked if we are to memorize this table, and I've given a couple explanations to it, but I do know that there's a better way, an easier way now, and I realize this. And it is understanding the direction between the source and the observer. So let's say that we are, first of all, let's focus on this equation right here. This is the Doppler shift equation, right? And one of the things that we're having issues with in this problem is understanding when to use the plus for the velocity observed, when you use the plus for the velocity of the source, when you use the minus. So this is an easy way to identify when to use plus or minus. So let's say that you have the source here, and this is the observed. The positive direction, let's just put it this way, the positive direction will always be from the observer to the source, okay? The observer, the positive direction is always going to be from the observer to the source. So if, for example, my direction, let me put it in red here, my direction for the source is going towards the observer, but my observer is moving away from the source, I can start writing my equation using the Doppler shift equation right here. Frequency observed equals frequency of the source. So velocity of sound, the speed of sound, I always say velocity of sound, but it's just the speed of sound. And notice that this is velocity of the observer, or speed of the observer, and this is speed of the source. Notice now that the observer is moving opposite of what I identified as the positive direction, because the positive direction always goes from the observer to the source. Therefore, my sign, my symbol is going to be negative. Now for the source, my symbol is going to be positive. I'm sorry, no. Actually, it's also going to be negative because it's also going away. It's going opposite of what I've identified as my positive direction. So both the velocity observed and the velocity of the source are both going to be negative, and hence I have identified both symbols. Okay, now let's do another example. Let's say that I have here and 2 points, and this guy is the observed, and this dot right here is the source. And let's put it more like, okay, so now I'm moving this way, and I am moving, the source is moving the opposite way. Like the rules I've said, the observers will always, the direction of the positive direction will always be dictated from the observer to the source. So I will always go from the observer to the source. That would be positive. And because it is positive, now when I write my equation, frequency of the observed, frequency of the source, v of the, okay, so speed of sound, and then this, the observer, is going opposite of my positive direction, so I go negative, but my source is going in the same direction as my positive direction. Therefore, my velocity of the source, my speed of the source, is positive. Okay, all right. Now let's go into another problem. Let's go to the 17-117. So this one asks us to solve the frequency from different perspectives. First asks us to solve the frequency of equal 1 as the observer, and then the frequency of equal 2 as the observer. So I'm going to do a line right here, just so I can split up. This is equal 1's territory, and this is equal 2's territory. And the scenario is always the same, but one changes from the observer to the source, and the other one, and vice versa. So I'm gonna do two dots, and both of them are always going against each other, but one changes. This is the observer, equal 1 is the observer, equal 2 is the source, and now in this situation, equal 1 is the source, and equal 2 is the observer. So, remember what I said, observer to source is always the positive direction. Observer to source is always the positive direction. Therefore, using my Doppler shift equation, I can easily identify that for the observer, since I am going in the same direction in this scenario for eagle 1 as a positive direction, then I have the observer eagle 1 is positive, and my source is negative because it's going opposite of my positive direction. The same goes for eagle 2. Notice eagle 2 is going in the same direction for the observer as the positive direction, and eagle 1 is going in the opposite direction of my positive direction, and therefore it is negative. You should get for eagle 1's observer is 4,200 hertz, and for eagle 2, 3,600 hertz. There you go. Okay, let's do one more, and let's do this RIT that I did for you guys, or at least for one of my earlier groups. Who knows, I might use this for later other students. Okay, so important. A taxi driver notices an ambulance approaching from the front, traveling at an opposite direction at 35.9 meters per second. The ambulance is emitting a loud siren of 475 hertz. The taxi cab driver perceives the siren to have a frequency of 515. Calculate the speed of the taxi cab. The taxi cab serves as the observer. The ambulance serves as the source because the ambulance is the one emitting that sound. And as you can see the wording here, the driver perceives the siren. So it means that the driver is the one that's observing the frequency. That's the case. It means that my positive direction goes from the observer to the source, and therefore I write down frequency observed equals frequency of the source, speed of sound, and since my observer is going in the same direction as my positive direction is positive, and since my source is going opposite of my positive direction, it is going negative. Therefore, we have our equation, and the velocity of the observer, taxi driver, is, or the speed of the observer is 10 meters per second. Done. All right, that concludes my Doppler shift class. I'll talk to you later.